g, where that is, of course, the multiplication of pointwise multiplication of functions, real valued functions, right? Not a dot product, it's just like e to the x times sine x or something. This is equal to VPF times g of p plus f of p times vp of g. Or if that bothers you, you could write it g of p, vp of f, plus f of p, vp of g. I mean, this is, I mean, fine. It's a vector space, so like technically, I guess I only have left scalar multiplication. Do you also want to define right scalar multiplication? I do, because I like to write scalars on the right too, right? I mean, it's true. Let's face it, it's nice to be able to write scalars on the left or the right. Whenever you have a left module, whenever you have a left scalar multiplication, you can define a right scalar multiplication just the same anyway, so whatever. This is the Leibniz rule. All right? And basically, all of this together, this makes VP a derivation. These are called derivations. Linear Leibniz is a derivation. Technically, it's a derivation on Cp infinity Rn. Is that right? Yeah. So can you tell me any derivations? So he's starting out, just like he did in section 3.2, for derivations on all of Rn, right? But we're actually interested in geometric sets, right? How do you find derivations on geometric sets? He describes rather carefully in this section how to do it, and I don't understand all of the nuances just yet, but essentially the story is going to be that we just look at f going from, S to R, instead of from Rn to R, where P is a point in S, right? So we'll look at functions from the geometric set to the from the geometric set to the real line, and derivations are going to take such functions and produce numbers. The meaning of these numbers is a directional derivative. I mean, this is the directional derivative. So basically, VP is something that tells me about the change in the function at the point. So we can think of vectors as being directional derivatives, is the point of this calculation back here. Let me see if I can be more specific. Let's look at an example here. Let me just be really. So we could have VP be like 1, 2, 3. All right. And let's say at P equals to 4, 5, 6. All right. Then this, excuse me, goodness gracious. I think in my rather pedantic notation would have been what? This, right? Is what I was doing before. So I should probably put some quotes on this one. Again, he wouldn't put the quotes because he's using the same symbol for both. But the derivation version of this, is going to be partial p is partial x plus 2 partial y plus 3 partial z. This is what we're going to derive, is that essentially you trade p comma ei for partial xi at p. This is what we want to derive. That we can write vectors in terms of the partial derivatives as being the basis. That's where we're going. It may not be readily apparent yet why that actually I mean, you can almost kind of already see it here if you work this out, right? So let's let's actually, you can kind of see it from this initial formula even. If we have VP as, I guess I should put quotes here. So if VP quotes is ABC, right? This is A partial F partial X plus B partial F partial Y plus C partial F partial Z, right? This is all at P, right? And so you could look at this as A partial partial X plus B partial partial Y plus C partial partial Z. This operator, right, acting on F. And so you see there's a natural correspondence between quote unquote ABC and this differential operator, A partial partial X, B partial partial Y, C partial partial Z. Evaluation at P, evaluation at P, evaluation at P, fine. And so these are the two dominant viewpoints of the tangent space, either as equivalence classes of curves to the object, or as derivations on the set of smooth functions defined near the point in question. You're like, smooth functions with respect to which domain? We've refused to choose a domain. We work with all possible domains which are defined on some open set about the point. This is called working with a germ of functions. He refuses to put this into typeset in the book, but that's basically all there is to it. Although I'm sure I'm hiding something. All right. But, you know, the question then is like, so I need to like dig into this tangent space concept, right? Further for you guys, I think. See, now I'm torn. I have things to say, but I'm trying to follow the book. Should make a choice, right? All right, I think we should go to section 3.5, actually. No, I should behave. It's the side cost of spending too much time on my abstract test, not having enough time to spend on your class. See, I'm trying to think about a good example. He's a little shy on examples in these sections. I mean, there's great examples in section 3.3, I think. Yeah. You know what? As good a time as any. Let me tell you what a manifold is. Because I think this seems to be basically missing from the book. And I don't know. He seems like he's dancing around the idea of it, but he's not quite. Maybe that's kind of the whole point of the book, is to not give this to you, but try to get the idea in your head about it. So what I'm doing is pedagogically unsound and wrong, and I shouldn't do it. But here it is. So this is a manifold M. What that means, really, I mean, is that there's these things called charts. So maybe this is U, maybe this is V. And there's these open connected subsets of M, which we call charts. And each one of these charts compared with a system of coordinates, all right? And the typical notation would be something like X and Y. Coordinates X and Y. And those will be mappings down to, you know, Rn. Maybe I should use Rk, but I'll use Rn. So I'm talking about an n-dimensional manifold. And so what it means is that M is some like topological space, whatever that means. It comes with this set of charts which covers the whole thing, all right? And what has to happen is that whenever you have an overlap between two charts, like this one right here, then if you study the map that goes this way, let's see, that way would be what? You say y composed with x inverse, right? Y composed with x inverse, restricted to the appropriate, I mean, I don't want to get into the details of that, but that's kind of where the fun gets, of course, this is only defined for the appropriate intersection points, right? But anyway, once you get through that, just that theory, then what are you looking at? You're looking at a mapping from Rn to Rn, right? And to say that the manifold is smooth is just to say that this transition function is smooth. That's what it means to have a smooth manifold. Actually, that's actually what it means for these charts to be what are called compatible. Then a smooth manifold is a set paired with a collection of charts which cover the whole manifold, and they're compatible charts. That's it. That's a manifold. Well, that's a smooth manifold. You could talk about a C1 manifold, then you just have that these are continuously differentiable. You could talk about a C2 manifold, these would just be twice differentiable. You could talk about a complex manifold that would put some kind of complex structure on these. You can put whatever kind of structure you want on the manifold by assuming that there's that kind of structure on the transition functions. But let's just talk about manifold for a second, all right? Then, so that's a manifold. The tangent space, all right? And then you could have another manifold n. Another manifold over here n, right? It could be n-dimensional, right? That would mean that, let me call this one x bar rather than y. It's not too late. And you can have another n-dimensional manifold, and you can have a mapping from here to here, f. You could have a function from one manifold to another. And then you could ask the question, what does it mean for that function to be smooth? What does it mean for a function from one manifold to another to be smooth? Well, if this is a manifold, then, if you pick a point, wherever over here, say P, and suppose this is f of P, right? Maybe there's some chart over here, I don't know. I should probably have called this U bar, right, given my bars. And so let's say that the chart over here is V. Sorry about the notes. So if this chart's V, that means that there's some kind of y down here to, Rn. And what it means for a function from one manifold to another to be smooth, what does it mean? Well, it means that this local coordinate representative has to be smooth. So again, down here, we just have, down here, we just have a function from, here would be x of P. And then over here, it would be y of f of P, right? And what would the local coordinate representative of f be? Follow the f is in the middle. I know that. Y, f, and then x inverse, right? X inverse takes me from here up to here. F takes me from there over to here. Y takes me back down again. And this, you see, folks, is some kind of, this is a function from Rn. Oh man, n. No. M. Oh, that seems so wrong, doesn't it? N is m-dimensional. M is n-dimensional. Sorry, it already happened. So from Rn to Rm, yeah, that's awful, but it is what it is. it serves my larger point, which is that the local coordinate representative of f, if you can get past your OCD, the local coordinate representative of f, I have trouble with myself, but the local coordinate representative of f has to be, well, that's a function from Rn to Rm, right? Which we have spent the better part of this semester already discussing, like how do you differentiate that kind of thing? What does it mean for it to be smooth? You calculate the Jacobian matrix. If all those partial derivatives are smooth, then that's a smooth function, right? So advanced calculus basically already has an answer for what this means to be smooth. So to say that a function on manifolds is smooth means that every possible local coordinate representative is smooth. So you might have multiple charts. You might have to check for different charts and different charts over here that each one of those possible representatives is smooth. This idea of checking multiple charts is not really in McNerney. He focuses on questions that are special to one specific chart, and that's fine, that's great. It's a good starting point, but I think it's worth us taking a couple minutes to talk about the more general idea. Because every once in a while it bleeds into my thinking, so now you'll understand me better. Then the other thing is, so that's great. What's the derivative? Where's the derivative work? Because you got to understand, these are curved abstract spaces. So you can't just replace points with vectors. You can't just move vectors around without willy-nilly. It doesn't make sense anymore up here. The tangent space at different points are really genuinely different. And so what happens is pretty simple, and this is what we're trying to describe in a slightly less abstract way, but you know, the tangent space is some kind of, it's not, I mean, I draw this picture, but honestly the tangent space might be better drawn up here, you know, TPM, and you know, I could draw over here the tangent space at f of p of n, but it'd probably be more honest to draw it up here because it's not, I mean, you can visualize it there, but they're really kind of detached. And then up here, we have what's called the push forward, which is the abstract version of the differential. And this differential, it is a mapping at the point P. It's a mapping from the tangent space to P at M to the tangent space to f of P at n. Now, what we're trying to do in this chapter is give concrete versions of these things for parametrized sets, for graphs, for hypersurface, for level set. So, I mean, he has the advantage of being concrete. He has the disadvantage of losing this big picture, I think, a little bit. Maybe that's not a disadvantage. Check this out. So, yeah.
What's that small little thing next to F?
That?
Oh, yeah.
Oh, just a star.
Is that the same as the star up there?
That one?
Yeah,
Yeah, same star, just star. So in the equivalence class of curves viewpoint, if I want to calculate like the push forward of, say, alpha prime of 0. Oh, you know what? I agree with you, Kang. That notation is horrible. Let's do what it is. Equivalence class at P. That's what it is. He's like, I'm not owning that. This equivalence class of curves at P, and the reason it's an equivalence class of curves at P is because if you look at P, right, this curve, and 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 that curve, and this curve, and that curve, they all describe the same stupid tangent vector. That's why it's not a curve, it's an equivalence class of curves that you have to work with logically. That lie is completely obscured in section 3.3. He relegates it to a homework. In so doing, his section gains greater conceptual, well, it gains greater clarity until you realize that this is an issue, at which point it throws into question everything he writes. So, which is not a bad thing. You know, there's stages of understanding that come here. Anyway, so what is the corresponding equivalence class of curves at f of p? Can you tell me? This is the differential for manifold maps. What? How do I take a, I mean, let me ask it in a different, sort of somewhat leading way. How do I take a curve here, you know, and produce a curve over here? See, if this is, you know, C, if this is the curve C, then how do I get over to here? Right? That's F composed with C. So this is F composed with alpha. That, in fact, defines the manifold theoretic analog of the differential. So it's not detached from what we're already doing, but the focus is different. Right now the focus is almost purely on geometry, and we're not really caring so much about numerical approximation of functions anymore, right? What we want, what the tangent space is it's sort of the best linear approximation to a curved surface. And these tangent vectors are ways to understand what that is. And if you're confused right now, it's okay. I'm going to spend the whole next class trying to unwrap this idea further. It took me a long time to really understand what tangent space was. But I'm not completely sold out to the book's idea that you shouldn't talk about abstract manifolds. I'm not sure it helps. So sorry I'm such a mess today. I'll try to behave better next time. Oh, I still have a couple minutes, I guess, but are there any questions? So what does that look like in the derivation viewpoint, you know? Enough for one day. Let's stop here. I don't want to. I'll stop here. I'll behave for once.